All right. So I think the last time, and correct me if I'm wrong, we got right pretty much to this example at the end of this. Is that right? And so what we just did, just to recap everything, because it's been, we've had the weekend and stuff like that. We basically introduced this concept of standing waves. We said, because we have the incident wave and the reflected wave on the line, they're going to interfere with each other. They're going to create this thing called a standing wave. We looked at a bunch of examples of it on a string. We looked at it in water. And then we watched the video where we had that kind of the oscilloscope and you could kind of see what was going on with the waves and that sort of thing. And what we derived was the magnitude of the standing wave. And we went through that math and we got some equation. And in the equation, it had like a cos term in there. And really one of the things we were interested in was, where is it going to kind of like peak out? Like what's its maximum, its voltage maximum, and what's its voltage minimum? And the ratio of that is called the standing wave ratio. So you can see it's V max over V min. That tells you a degree to which you've got these standing waves on the line. Because if your V max is big and your V min is small, it means it's really varying down your line. If the V max is pretty close to your V min, then that ratio there is going to be kind of close to 1, not that big. And that is generally a good sign that you don't have a lot of reflections on the line, that things are matched. And matching is going to be kind of a big topic for us going forward. So we have our standing wave ratio. We have our definition, the V max over V min, and then we have how you're actually going to calculate it, like how you're actually going to plug the numbers into it. You can just use gamma. Okay, so let's do an example. Go through the book. Examples 2.5 and 2.6 would be a good one. Make sure you're, calculating things yourself. You're not just kind of doing too much, just kind of looking at it and go, oh, okay, I kind of see. Like actually punch the numbers in yourself, like, and really look back and like, where did this come from? Why did they do this? That sort of thing. So here we go. 140 ohm lossless line is terminated in a load impedance. ZL equals 280 plus J 182 ohms. If lambda equals 72 centimeters, find a bunch of stuff, okay? So you need to translate this, okay? What's Z naught? 140, right? This is the way that you say what the characteristic impedance is. If you wanted to say that kind of fully explicitly, you would say a transmission line with a characteristic impedance of Z naught equals 140 ohms. Probably that's not going to happen too often. Instead, you just say 140 ohm line. And the word lossless there is important. So immediately you know some stuff, right? So in your head, you go, okay, I can use some of those simpler equations. Some things equal 0. Which things? Well, maybe on your formula sheet you'll have that, or maybe you remember. In terms of our R prime, L prime, G prime, C prime of our transmission line parameters, the R prime and the G prime are going to equal 0. It's terminated in a load impedance, so we're given ZL. If you remember the last example that we had to calculate that part. Like we had a resistor and it was in series with a capacitor, right? And we were given the value of resistance and the value of capacitance. We had to figure out what the imaginary part of the impedance was, because you can't just use the capacitance. We had to use 1 over J omega C. Okay, if it was an inductor, we'd have to use J omega L, because the impedance of an inductor or a capacitor depend on what frequency you're at. Like for an inductor, its impedance at DC is 0. It's a short circuit. J omega L. Omega is 2 pi F. F equals 0 at DC. 0 impedance for an inductor. Okay. Similar things, but kind of opposite for the capacitor. Here, we don't have to do any of that. You just gave it to us. That's nice. One less thing to calculate, right? We would know, though, it's kind of equivalent to an inductor because it's plus, right? The impedance of a capacitor is minus J over, or 1 over J omega C, or minus J over omega C. So it's that minus. So if it's the real part's like a resistance, the imaginary part's either like an inductance or a capacitance, depending on whether it's positive or negative. Given ZL, we're just given lambda, right? We're not told the frequency at all, but we're given lambda. first things first, we want to find the reflection coefficient. All right, so A, we want to calculate gamma. We really only have one formula that we've been using to calculate gamma, and I've said it a bunch of times. Hopefully it's starting to kind of like sink in. It's the ZL minus Z naught over ZL plus Z naught. We know Z naught. So our ZL is 280 plus J 182 minus our Z naught, which is 140, divided by ZL again, 280 plus J 182, but this time it's plus Z naught, so it's plus 140. So you can add together the real parts. So 280 minus 140, well, that's just going to be 140. We still have our plus J 182. And then on the bottom, we have 280 plus 140, so that's going to be 320. So we've got, 420. And we have plus J 182. Okay. Now, I'm hoping that you're getting faster at these. All right, hopefully you're getting pretty quick at these things. You're definitely going to have to do some of these calculations during the midterm. And like I said before, you can't take forever on it. Like there's, you got to be able to do these kind of quickly. So make sure you're getting lots of practice at them. Convert to polar, right? Convert the top number to polar, convert the bottom number to polar. If you did that, I think you'd get something. Tell me if you get something different, but like 229.6 angle 52.4 degrees and 457.7 angle 23.4. And if it's still a little fuzzy about how I did that, question? Yep. I'm okay with it because some people, you can do it in the calculator. However, the more steps that you skip, if you make a mistake, now you're giving up the opportunity for part marks. For instance, if you wrote that and then just wrote equals something, and that something was wrong, you're not going to get many part marks for that, right? You might get a little something of like a pity, fraction of a mark for writing the right formula down, but I didn't see anything. Whereas if you did that, and then 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 in the final step, you just got the wrong number because you just punched into your calculator wrong, you would just get a very, very small deduction, right? Because you just made a very, very tiny error at the end, and I know you knew all the steps and you just made a simple mistake. Versus if you just write that and then write a wrong number, I don't know anything, right? It's hard to give part marks for that. So just keep that in mind when you're answering things. Okay, so how did I get this? I got to get the magnitude. That squared plus that squared, square rooted. That would be the 229.6. The magnitude, this one, the 457.7, 420 squared plus 182 squared, take the square root. It should be that. To get the angles, imaginary part divided by the real part, inverse tangent, make sure you know what mode your calculator's in. Are you in degree mode? Are you in radian mode? Doesn't matter which, just make sure you know. Question? Oh, so we just square that one plus that one, this one squared. So we don't square it twice. We just do like 140 squared plus 182 squared. Then we take the square root. It's really the Pythagorean theorem. If you think about it, it's like we've got like x-axis is real, y-axis is imaginary. Put it over rad twice. Yeah, when we convert. Which part twice? So let me walk through this and you stop me wherever. Okay. Talk to me afterwards then, and we'll sort it out. Okay. Or if you see exactly where the confusion is, let me know. Because basically, just to recap, that squared plus that squared square rooted is that. That squared plus that squared square rooted is that. 182 divided by 140, inverse tangent with calculator in degree mode is 52.4. Double check your signs, plus, plus, we're in quadrant number 1. We don't need to do any monkey business with the 180, plus or minus. 182 divided by 420, inverse tangent, 23.4 plus, plus, don't need to adjust anything with 180s. We're good to go. Now, that number divided by that number. Now that we're in polar over polar, we can just divide the magnitudes and do the angle, the top angle minus the bottom angle, okay? So it would be 229.6 divided by 457.7, which you'd get something pretty close to 0.5, I think, right? And then the angle would be 52.4 minus 23.4, so that's gonna be 29. Okay, any questions about that? Anybody get anything different? Okay, I'm going a little quicker now because we've been doing these a little bit. Hopefully you've been doing some of the quizzes and stuff as well. Now, you could convert that back to rectangular form, but for gamma, for the reflection coefficient, it makes more sense to me to leave it in polar form. You're not going to get deducted any marks. It's equivalent. It's just two different ways to write the same thing. The reason why this is nice is because that tells you immediately how much gets reflected. If you have like a 1 volt amplitude coming down, it hits the load. If the magnitude of your reflection coefficient 0.5, the reflected wave amplitude is going to be half the incident wave amplitude. It'd be half a volt. That's why if it's in real plus J imaginary, it might not be so obvious. Okay, so we're good on part A. Everybody's good on part A. Okay, part B, the standing wave ratio. So this one's pretty easy after we do part A. We just use that formula. We already calculated gamma, and we had it already in polar form, which is the magnitude of gamma with an angle of gamma. So the magnitude of gamma is just 0.5. So we just have S equals 1 plus magnitude of gamma over 1 minus magnitude of gamma. 1 plus 0.5 divided by 1 minus 0.5. So that's 1.5 divided by 0.5. So that's 3. All right. Now we get to the locations of the voltage maximum and the voltage minimum. This is where things get a little more interesting. So we did this at the end of last class. And this is really what we're saying here is kind of remember what I said at the beginning where the standing wave ratio is this maximum divided by the minimum. Well, this part C is really asking, like, you got some transmission line, where is the maximum occurring, right? So we got to figure that out. And it's periodic. It will continue happening every so often, okay? So let's go back and we'll look at the formula for this. Where are we here? Here. D max, distance where there's a voltage maximum. And we got this kind of ugly thing to deal with, right? We got this conditional statement, we got a bunch of stuff. So the best way to handle it is just look through the equation, make sure you know what each thing is, and ask yourself the question, do we have that? Yes or no? And if we don't have it, can we calculate it? Yes or no, right? So we'll look at this, and well, the denominators are good, 4 pi and 2, so we don't need to worry about those, right? All right, lambda was given to us in the question. It was 72, I think, centimeters, right? So because of that, we've got lambda directly. Now, that's being nice. We could have had the question where it didn't give us lambda, but you had to calculate lambda. And we're able to calculate lambda with UP over F is one of our equations for that. But then we would have had to give some more information. We would have had to give a way to determine what UP is, and we would have had to say what F is. So those weren't given, so not much we could do about that. Does anything in this question tell us what UP is? No, this is great. That's exactly the response that I wanted. So it says it's lossless. So a very common thing is to go lossless. That means we know what the speed is. It's like the speed of light or something like that. But no, just because it's lossless, it still could have a different velocity. So we don't know the velocity. We know it's lossless. It could be air. It could be like, in other words, the dielectric could be air, in which case the speed would be the speed of light, but we can't assume that. All right. So just put a little thing in the back of your head. Lossless does not equal like UP equals C or anything like that. Okay. So what else we got in this equation? Where are we here? We are here. Theta R. That's the only thing we don't know. N is the thing that just repeats itself, right? And then we have to deal with this business of, oh, is it N start at 1 or is N start at 0? But we'll talk about that in a second. What is theta R? Yeah, it's a phase angle of gamma. R is for reflection coefficient. That's the angle of gamma, which we already got, right? So we know it. So we know everything. What was the value we calculated for theta R? 29 degrees. Now, we're going to have to punch a number in here. Do you think we should punch in 29 for theta R as in degrees? Or do you think we should put theta R into radians first? Yeah, it's the pi's really give it away, right? The pi says, oh, this thing's in radians. I need to put my theta R in radians, okay? With that, the only thing we have left is this business. Does N start at 0? Does N start at 1? Yeah, because you just ask yourself a simple question. What's theta R? We said it was 29 degrees. 29 degrees is bigger. 29 is bigger than 0. So it starts at 0. And again, the reason why we have this business here of this or this is, imagine for a second it was minus 29 degrees. All right. Just the gamma was different and it was minus 29. If we started at 0, then N would be 0. That would be gone. We'd have a negative number here because theta R would be negative 29, which means our D max would be negative. Makes no sense. Remember last time, I think we talked about how a negative D is beyond the load, which makes no sense at all. So this whole comparison business here is to basically ensure we don't get a negative D max because it doesn't make sense, okay? So all we have to do now is plug in the numbers. Okay, so let's do it. So let's go D max. We're on part C here, so C. D max is theta R lambda over 4 pi plus N lambda divided by 2. And we've already said it's for N equals 0, comma 1, comma 2, comma dot, dot, dot. So let's plug in the numbers. So we got 29 for theta R, but we have to convert it to radians. How do we do that? Pi over 180. Pi over 180 times lambda. Now, what's lambda? What should I put in here? Yeah, so I think everyone got that. So it's in centimeters. We just got to put it in meters, right? So it's 0.72 divided by 4 pi plus N. And then again, we have our 0.72 divided by 2. Okay, so you punch that into your calculator. The pi's are going to cancel out there. I think you'd get something like, if I did it in centimeters, the answer in centimeters, like 2.9 plus 36 N centimeters. So if you had it in meters, it'd be like 0.029 plus 0.36 N. and it's for n equals 0, comma 1, comma 2, comma dot, dot, dot. So all we did was really plug the numbers in there, make sure we're in radians, leave the n as just kind of a variable because it just increases. Any questions about that one? So what would our D max 1 be? Yeah. That says if this is the load here, D goes from the load back to the source. If you put your ruler on here and you measured 2.9 centimeters, that's the point at which there's the most constructive interference, and you would expect the total voltage at that point, the magnitude of the voltage, to be a peak, to be the maximum at that point. Okay, last part of this question, we want to get D min. Now, the way that we said is easiest to get D min is just get D max, and you either add a quarter of a wavelength or subtract a quarter of a wavelength. So the only question here is, do we add or do we subtract? To do that, we just have to ask ourselves this question. Is D max, and this really means the first D max, the one that we just said was 2.9 centimeters, is it less than lambda by 4 or greater than lambda divided by 4? So we need to know, what is lambda divided by 4 for our example. And in the question, it gave us lambda is 72 centimeters. So it's just 72 divided by 4. So what's that? 72 divided by 2 is 36, divided by 2 is 18. So now we have numbers here. So this is really our D max 1, which we said was 2.9 centimeters. And we know what our lambda divided by 4 is. It's 18. So then you just ask yourself the question, is 2.9 less than 18? Yes. So we use this one, which really just means we use the plus. If you didn't do this, let's say you just guessed, you didn't know how to do this, you forgot, and you guessed. Let's say you guessed wrong and you guessed this one, right? Our first D max is 2.9 minus lambda divided by 4, which is 18. Then you would calculate your first D min to be 2.9 minus 18. You get a negative number. Again, doesn't make sense because it's beyond the load. So again, this plus minus condition business is all just to make sure you don't get a negative number. Okay, so we know we have to use the plus for this case. So here we go. So D min is D max plus lambda divided by 4. And so what's that? Well, our D max in general is the 2.9 plus 36n, if we're doing it in centimeters. And then plus lambda divided by 4, that's 72 divided by 4. And so the whole thing would be just 18 from here plus 2.9. So that'd be 20.9 plus 36n centimeters for n equals 0, comma 1, comma 2, comma dot, dot, dot. And just like the other one, what this means is if you had your load here and you wanted to know where the voltage minimum on the line is, if you wanted your first voltage minimum, you plug in n equals 0. That would kill the 36n. And you'd be at 20.9. So you'd lay your ruler on here, starting at the load and going backwards towards the source. And where you measured 20.9, you go, at this point, that's where we get the most destructive interference between the incident and the reflected waves. And that's where we're going to have a voltage minimum. Okay. And then they repeat themselves. It goes maximum, minimum, maximum, minimum, maximum, minimum. Okay. It repeats itself as after each half wavelength. Any questions about this one? Yeah. Only for D max 1. in other words, the first D max. You're starting at the load, you're going back to the source. How far do you have to go until you reach the first maximum? So in general, it is the full thing, the plus 36n, but the first one from the load, it's just 2.9 because n starts at 0. Any other questions?
We leave it like the plus 36n on the test, is that right?
Yeah, it would really depend on what the question asked. If it just said, find the D max or something, then that would be fine. If it said, sometimes I get specific and I say, find the second voltage maximum from the load or the first voltage maximum or something like that, then you would need to know that, oh, I need to plug in like 1 or 0 or whatever in for n. Yeah. Any other questions? All right. All right. So that is the end of the standing wave stuff, but we're kind of carrying on in the same sort of realm, because what did we just find? We just saw that the voltage, and even though we focus on the voltage, the current does the same thing. They change for different points on the transmission line. Like we just figured out, where's the voltage maximum? Where's the voltage minimum? That implies the voltage is changing on the transmission line, depending on where you're at. Going along with that, the current is changing as well at different points in the transmission line. What's impedance? Ohm's law, V equals IR, right? R equals V divided by I, or if you like, Z equals V divided by I. So if you thought, instead of thinking in terms of voltage, if you thought of impedance, you'd be like, well, what happens with the impedance on the line then? And the answer is, as we're going to go through the math, the impedance changes on the transmission line as well, okay? Like I think I talked about the last time, you could have a short circuit here where you just kind of connect the center conductor to the outer one. And if you're right at the load, well, it does look like a short circuit. But if you come back a little bit, like a quarter of a wavelength, like in that last example, that was like 18 centimeters or something like that. So it'd be like that, well, maybe like that. That short circuit, it doesn't look like a short circuit if you're looking towards it. It actually looks like an open circuit. That's as different as you can possibly get from a short circuit. That's completely opposite of a short circuit. So the big picture here is we got these incident wave, reflected waves, they interfere with each other. They cause a standing wave. That means the voltage changes as you go at different positions on the transmission line. The current also changes at different positions on the transmission line. The ratio of the voltage to current then changes as different positions on the transmission line. So the impedance totally depends on where you are on the transmission line, okay? So we want to be able to calculate that, because this is like a critical thing. Because if you're going to connect something at some point on your transmission line, it'd be nice to know what the load is, right? Like you have a load maybe at the end, but what we're going to see is, depending on where you're looking towards that load, the actual transmission line itself totally changes what it looks like. We need to know that, right? Or else the thing you design might not work at all. All right, so we're in 2.7 and 2.8. And this is pretty much what I just said. The impedance varies with position on the line. We've got our source. We've got some source impedance. We have some transmission line. We've got some load. I'm not sure how much in your previous circuits classes you've talked about like impedance looking into, or like looking in a certain direction, or like looking towards the load, or like looking from a particular point in a certain direction. Like there's a bit of that in 340. In 340, especially when you're looking at how many of you have done 340 or are currently doing it? It's not that many, okay. Anyway, in 340, it's really heavy on the transistors. You get introduced to transistors, BJTs and MOSFETs, and you learn how to design amplifiers with them. And so for the BJT, there's a few common configurations, and for the MOSFET, there's a few common configurations. They're called, you know, common source and common gate and common drain or source follower. And when you're analyzing those, you're often like, what's my input impedance? Okay, what's my output impedance? That sort of thing. Kind of similar here, but the main thing is we have to know which way we're looking. Okay, so you can see Z in, this is the input of the transmission line. This is where the transmission line's connected. So Z in is like, I'm looking into the transmission line. Now in 340, like I was just talking about, as we've said, we pay no attention to transmission lines. So any kind of interconnect, we just completely ignore. And the input impedance, if this was like 340 kind of style to this, Z in would just equal ZL, because we don't consider the effects of the transmission line. But we know our condition, if you go back a few weeks now, when we have to worry about transmission line effects or when we don't. And we're obviously studying the case when we do. And so what Z in really means here is, what's the input impedance, taking into account some length L of transmission line with a load ZL connected to it. We'll also say, like, well, what if we're interested in some midpoint? It doesn't have to be exactly in the middle. It could be at any point on the transmission line. We might be just like, well, say I stopped there and I was looking towards the load. What would that impedance be? We'll kind of call that like a Z at some distance D, although I don't like that I'm using D there because down here it says D equals L. But basically, I just mean at any point on the transmission line, looking towards the load, we are going to have an equation to be able to calculate what that impedance is. Okay, how do we do it? Well, you might guess we just use Ohm's law, just like I just said. And you're like, well, that doesn't look like Ohm's law to me. And yes, it doesn't, but you know, hang on, this looks like Ohm's law. Like I said, Z equals V over I. We know it's a function of position, because that's what everything we've been talking about. Everything changes at different points on the transmission line. And everything we've been doing is dealing with the phasors. That's why the little tilde is over top. Then you could say, well, what is the expression we've been using for voltage? And you could say, well, we did use one where it was like V at, well, I think we did it at V at Z. And it was like V0 plus e to the minus j beta Z plus V0 minus e to the plus j beta Z, something like that, right? Maybe that one looks familiar. But then remember what we did the last time. We said, well, we know what, just from our definition of gamma, which is V0 minus over V0 plus, we know that V0 minus equals gamma times V0 plus. So if you remember that one, we basically plugged that value into here and then factored out the V0 plus, okay? And the only other thing we did was we said that D equals minus Z. That's why I have a minus Z here, but it's a plus D there. All that to say that this thing on top here is just the same thing we've been looking at for weeks now. All right, where did it come from? All right, let's retrace our steps. So this came from this, right? Where we just hadn't plugged in the gamma V0 plus yet. Okay, so then where did this one come from? That was our solution to the wave equation. And what was the wave equation? The wave equation was that one with the second derivative in it. And we needed some voltage form that would satisfy that. It equaled zero, had to equal zero, right? And this was our solution to the wave equation. So where did the wave equation come from? The wave equation came from our Kirchhoff's voltage law and current law. We came up with an equation for each of those, and we took a second derivative and we plugged it in, and we came out with the wave equations. And then you could say, well, where did the Kirchhoff's voltage law and current law stuff come from? That came from our transmission line model with the R prime, L prime, G prime, C prime in it. And then we have all the equations to calculate the R prime, L prime, G prime, C prime. That's kind of the whole progression there. So that gives us this numerator. The bottom is the same, it's just for the current. We've just mostly been focusing on the voltage, but all along there is also a current one. The only difference is we've got a minus sign, and this one is divided by Z naught, which is where that Z naught comes from. All right, we could just do one simple thing then. We could just say, what if we factored an e to the j beta d out of the top and out of the bottom? Like we pulled it out, an e to the j beta d. Well, that would just go to 1, right? Because we pulled it outside. So that's that. And then we're pulling another e to the j beta d out front. So it goes to 2, minus 2. And then you could do the same thing on the bottom. That again would be 1. That would go to 2. And then outside here, you'd have an e to the j beta d over an e to the j beta d. They'd cancel out. And so this is the same as that. It's just written in a slightly different form. Right? Okay, you're probably not going to use that form very much. I'll show you the one that you're actually going to use all the time. Not that you couldn't use that, you could. So what we're going to do next here is say, like, this thing here and this thing here, it's gamma times e to the minus j2 something. So what we can call this is just gamma d. So that's all we've done. We just kind of like replaced what was in the previous formula with a gamma d. D meaning it is a reflection coefficient, but it's at some position d on the line. We're not usually that interested in gamma d. Normally, when we talk about a gamma, we are talking about the reflection coefficient at the load. And if you think back to where did reflection coefficient come from, it was right when we had that whole thing where I was like, let's make the load at z equals 0 because it'll make our life easier. And then we could plug in z equals 0, and we ended up rearranging an equation and getting this thing that we defined as gamma. In other words, gamma all along is gamma at the load. Our reflection coefficient, whenever I just say reflection coefficient, it means the reflection coefficient at the load. But you could think about a reflection coefficient some distance away from the load. Again, we're not going to do that too much, but it's more just like a stepping stone to get to the formulas that we're really going to use. So if we did that, well, we could kind of throw it in this equation here. It's just gamma d. And then from there, well, we can do some more manipulations here and figure out an expression that's kind of, it's not easy to use, but it's maybe easier to use. So here we go. If we've got this as our ZD, so look at that drawing up at the top right, okay? Like before we even talk about the equations more, the important thing here is that you have a picture in your mind of what's going on, okay? So top right, we've got a circuit. It's got some generator voltage. It's got some generator impedance ZG. It's connected to our transmission line. We've got our input to our transmission line right at AA prime. Right at CC prime, a load is connected. Who knows what it is? It's some load, it could be anything. And what we're driving towards here, what we're heading towards is an equation for the impedance at any position D in between the load and the input, okay? Which means if we somehow, and we're gonna have an equation for this shortly, are able to calculate Z of D, then that is what the input impedance is at B prime, looking towards the load. Inside that calculation, whatever effects the transmission line's doing, right? due to the incident wave and the reflected waves and standing waves and all that kind of stuff. All of that is going to be baked into the equations that we are going to derive for Z at D. So if we calculated Z at D, which is at this point right here, what we're doing is we're looking towards the load at BB prime, and the calculation for that input impedance takes into account the effect of this section of transmission line from B prime to C prime and the load ZL. So it's all baked into that impedance, which means we can replace our circuit with this, okay? So we still have our voltage source. We still have our generator impedance. We're still connected at AA prime to our transmission line. We didn't deal with this section at all, right? We didn't do anything between AA prime and BB prime, but everything after BB prime is baked into Z at D. Does that make sense? Any questions about that? And then you could say, well, why stop at BB prime? Why not go all the way back to AA prime? And we will. And that's often what we're interested in. And then if you did that, we completely removed the transmission line from our circuit. But all the effects of the transmission line, the reflected waves and all that stuff, is all within Z at D, because the way that we're calculating Z at D is voltage divided by current, and the expressions we're using for the voltage and for the current include the incident wave, the reflected wave, the reflection coefficient, all of that stuff. So how do we calculate this? Well, we just saw this on the last one where we just called the thing gamma D. And we could go all the way back to the input, like I said. So the word input impedance usually means like the input of the transmission line, which is at AA prime. But be careful if you're ever doing an exam or something and you're not exactly sure where you're supposed to calculate the input impedance. Because you could say, what's the input impedance at BB prime? Or you could say, what's the input impedance at AA prime? If it just said, what's the input impedance, you would just assume that it meant at AA prime, okay? Okay, so we could also go all the way back to the input. So this is like we go all the way back to the input, okay? This is exactly what we just had, but we don't have any intermediate BB prime. We just have our whole length of line. The whole length of line is L. If we calculated Z in, we could replace the whole thing. Note there's no transmission line in this circuit. If we have included the effects of the transmission line in Z in, now you're back in circuits land, right? Like 240, okay? Your basic circuit analysis. Because anything to do with the transmission line is inside Z in. Okay, so how do you actually calculate it? There's a bunch of formulas. I'll show you the one that I like. I don't like these ones that much. There's nothing wrong with them. You can use whichever ones you like. Just if you use these ones, it's a little ZL, okay? The little ZL is the normalized load impedance. So the little ZL is the full load impedance, okay, divided by the characteristic impedance. So just be careful about that. It's easy to make a mistake. I don't like these forms because they all have the little ZL. We're going to use the little ZL when we get to the Smith chart. But for now, I'll just write this the way that I like it, which is without the little ZL. Basically, you just multiply the top and the bottom by Z naught. So just make sure, I will try to write the little ZL without the little cross in the Z, so you can tell by my writing, because otherwise it's hard to tell. These are the full non-normalized ZLs. Like in our last example, I think it was like 280 plus J1 something or other, right? That's that ZL. But if in terms of our last example, if you were dealing with the little ZL, it would be 140 plus J whatever divided by 140. Okay. This one is just straight impedances. So how would you calculate it with this, right? I think we'll do an example shortly, but let's just talk about it. Z naught, we know that, right? Normally it's a 50 ohm transmission line, blah, 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 right? That's Z naught. So boom, 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 we're good there, okay? ZL is normally given. You normally know what is connected at the far right of this thing. So you normally know ZL. It could be 0, it could be infinity, it could be 140 plus J, 182 or whatever, okay? It could be anything, but you usually know ZL. So the only thing left in here is tan beta L. So what's L? Okay, it is. So in this case, the L is the full length of the transmission line, which is the distance from the source. Yep, but we're going all the way back to the input, to AA prime. So that's L away. It just has units of meters. It really is just, you take your whole length of line, you get your ruler out, and you measure the full length of the line. Okay. Very often L is given too, because you have to know how far, right? So beta. Someone hit me with an equation for beta. 2 pi over lambda, that's a good one. That's the one I always remember. There's other ones as well, but 2 pi over lambda is nice. In order to calculate lambda, beta, we would need lambda, right? So we'd have to figure out a way to get lambda. And if we were given enough information to calculate lambda, we'd multiply it by L. We'd take the tangent of it. We'd multiply it by whatever Z naught is. Note that J there. That gives us some complex number up top. Likely it's going to be in rectangular form. Same thing on the bottom, some complex number, likely in rectangular form. Convert them both to polar form, do exactly the same thing that we just did. And then at the end of it all, multiply it by Z naught. You're going to get some complex number. That is the value of impedance looking into the transmission line. And from there, we could replace the entire transmission line with Z in, where Z in is given by this thing, because this includes all the effects of the transmission line. Okay. Any questions about that? Okay. Give this some thought and do some practice problems on it. We're going to do an example, but this tends to, when I throw some questions like these on the exams, it tends to throw people off a little bit. Like sometimes they're really simple. I think they're really simple, and then it doesn't go so well. But let's keep going here. So this is the equation for Z in that I like, and we'll use it in an example shortly. But if you like the others, they should all give you the same number. Okay, so what I was saying before was if we calculated Z in, and within Z in, it fully included all the effects of the transmission line, then we could come up with this simpler circuit, where now we have a voltage source, some impedance associated with that voltage source, and a load. This is like a circuit, a basic circuits question, right? And we could figure out what VI is. In other words, the input voltage, because it's just a voltage divider now. So it's a regular old voltage divider. So how do you do voltage divider? Well, that would just be like Z in over Z in plus CG times this voltage over here, right? If you like, imagine instead of these boxes with Z's in them, imagine them being resistors, right? And then it might become more clear that, oh yeah, if I just wanted the voltage across a resistor here, I would just do that resistance divided by the sum of these two resistances times the voltage over on this side. Okay, same thing, just with these impedances. So that's what we have here. So we're able to get the input voltage. It's VG times Z in divided by Z in plus ZG. That's it. Okay. And last thing, we won't use this too much. There might be one quiz question on this, but if you notice, we never had an expression for V0 plus. What is V0 plus? Yeah, that's good. You even said the phase there, because normally I just say it's the amplitude, but it is the phase as well. You have an incident wave, it's a voltage wave. It's got some amplitude, right? Whatever it is in volts. And it could have a phase shift as well. You can think about it as the amplitude of the incident wave. We've never really had an equation for that one. We had an equation for V0 minus the amplitude of the reflected wave. We said it was gamma times V0 plus, but we never had an equation for V0 plus. So if we use our regular old equation that we have for V at Z, right? And we use what we know now as V at I, which is the voltage at minus L. So basically we just plug minus L in for Z. Then we have two expressions for VI. We have the one at the top, which is circuit, basic circuits, it's voltage dividers. And then we have this one, which really all came back from our solution to the wave equation. We can set them equal to each other because they're both VI, and we can solve for V naught, and we get this thing here. We're not going to use that all that much, but at least now we kind of completed the picture where all of the things that we introduced, we can calculate them. So really all that this is there's a voltage divider going on, right? Because we have this internal source impedance, and then looking into the transmission line and the load, that's some other impedance. We're calling it Z in. And so some of the VG drops across that, and then the rest travels on down, and we've got a few modifying things there, so we just get the V0 plus. All right. We're not going to use this equation too much. The one we're going to use more is this for Z in. Okay. Now you can use this not just when you're going all the way back to the input, but basically if you just, instead of L here, you just put in wherever you are going back to. Like if this is your line and you want to go back to the middle, you can use this equation. You just go, well, whatever that distance is, what is L to get me to the place where I want to figure out what the input impedance is. All right, so let's put some numbers to all that, okay? 2.7, make sure you're going through that, do the calculations yourself. And let's do this example. How are we doing on time here? Yeah, 15 minutes. We should be able to get through this pretty well. A voltage generator. Just like you would in a lab, you go to the signal generator, right? You turn it on, sine wave, set it to some frequency, set it to some amplitude. What would the amplitude be of this? 5 volts, right? This goes all the way back to the early days when we had a capital A out in front. It was like A cos blah, 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 right? All right, so this is our generator voltage. So don't try to keep everything straight here. It's a generator voltage. It's a function of time. You might say, well, isn't that also a function of like position? No, because we're not talking about the voltage anywhere on the transmission line. We are just talking about this voltage source, like the box on the shelf that is putting out a voltage, okay? All right, so that is our source voltage, our generator. It's got an internal impedance of ZG equals 50 ohms. It's connected to a 50 ohm lossless airspace transmission line. Do we know the velocity of this one? Yes. So that's the magic piece right there, the airspace, because what that means is the wave, the electromagnetic wave, even though we've been talking about in terms of currents and voltages, the electromagnetic wave is traveling in the dielectric between the two conductors. And the electromagnetic wave is traveling then in air. And an electromagnetic wave in air is just the same as light in air, travels at the speed of light. So that's airspace tells you speed of light, lossless tells you, oh, we can use all those simpler equations that we derived not too long ago. The line length is 5 centimeters. The line is terminated with the load impedance of 100 minus J100. All right, let's calculate some stuff. Okay, we want the reflection coefficient at the load. Now, as I said, the reflection coefficient, as we've been talking about it, is at the load, okay? So it's our regular reflection coefficient. ZL minus Z naught over ZL plus C naught. All right, so what do we got? ZL is 100 minus J100 and minus 50. 100 minus J100 plus 50. All right, so 100 minus 50, that's 50 minus J100 divided by 150 minus J100. All right. So you go ahead and you flip that over to polar, just like we've done several times now. And I'll just come over here. And so if you did that, what would you get? Well, first of all, let's look here. We got a real minus an imaginary for both the numerator and the denominator. So when you punch that into your calculator for the phase angle, do we need to do anything to it? So which quadrant are we in? So punch it into your calculator and let's see what it spits out for the numerator, let's say. So I just wrote down the magnitudes, but to get those, it would just be like 50 squared plus 100 squared. Okay, so we get a negative 63.4. So what quadrant is that in? That does agree, right? So we don't need to do anything. Quadrants 1 and 4, we don't need to adjust it. You don't even need to remember what quadrant you have to adjust it for if you just ask yourself at the end of the day, does my angle agree with the, real and imaginary part? In this case, you got minus 63. So you're going down in the x-axis. You're in that quadrant 4. And it was 50 minus J100. So you're to the right and you're down. They both agree. Both quadrant 4, we don't need to do anything with it. Okay, and the bottom is also going to be in quadrant 4, and it's going to be something like minus 33.7, I think. Anybody check that? Sound good? So here we can just, if you ever get a gamma magnitude greater than 1, you know you've made a mistake, right? Because we talked about that before. That would imply somehow that it's grown, like it's reflected off of something and it's like been amplified. So just a little check. So we would do 111.8 divided by 180.3, something like 0.62, something like that. And to get the angle, we would do minus 63.4 minus 33.7. So we get like minus 29.7 degrees or something like that, okay? All right, we've done a bunch of these, so I went fairly quickly through that, right? Now we can get to the more interesting part. We want the input impedance. We have an input impedance formula, so let's use it. I'll use the one that I like. Z in equals Z naught, ZL plus J, Z naught, tan, beta L divided by Z naught plus J ZL tan beta L. So we kind of need to go through all the parameters in this, see what we got, see what we're lacking. So what is Z naught? 50. We know that because it says it's connected to a 50 ohm lossless airspace transmission line. That means Z naught equals 50. What else do we need? We need ZL directly given to us. It could have given it to us as a circuit, right? Where we have a resistor in series or something with an inductor or a capacitor. We're told the frequency, and you'd have to figure out what the impedance is. So make sure you can do that. (100 minus J100 ohms). So we're looking good here. We got the Z naughts, we got the ZLs. All we're left with is the beta L in the tan. So L, what would L be? 5 centimeters. So this is an example here where it says, find the input impedance, and it just gave you the total length of the line. So the line is only like 5 centimeters, so it's only like 2 inches, right? So when it says find the input impedance, what that is saying is find the impedance at the input of the transmission line, which is 5 centimeters from the load. So L equals 5 centimeters. Oops. Equals 0.05 meters. Just put everything in meters, don't forget that. All right, so all we're left with is beta. We just have to find beta. Well, what could we do for beta? Beta, well, it equals 2 pi over lambda. We could go down that road to find lambda. We could do it. How would we do it? Lambda equals UP over F. And the question would be, do we know UP? What is it? Right, 3 times 10 to the 8. Do we know F? What is F? Yes, so this is omega, because it's always omega t. And then I always just remember that omega equals 2 pi F. So F equals omega divided by 2 pi. So 2 pi times 10 to the 9 divided by 2 pi, okay? So we could do it. We can calculate lambda, then we calculate beta, 2 pi over lambda. Or you could, look in the book or look at your formula sheet, and you'd see another equation for beta that's totally equivalent, which is that. The only difference with this one is, well, we can just plug omega in directly because it's omega t in the equation, and UP is just C. But really, if you plug them in, you'd see, oh, these are perfectly exactly the same thing, right? Because 2 pi's, cancel out or whatever. So, yeah, it doesn't matter which one we do here. Let's say we did the omega, which is 2 pi times 10 to the 9 divided by 3 times 10 to the 8. Okay. So you punch in that into your calculator. And if you wanted to keep it precise, you could keep it as 20 pi over 3 radians per meter, or you could just get that into a number, right? Okay, that's good. Now, you're free to just plug everything in right now, but it's easy to make a mistake with this one. There's lots of traps here. If you wanted to make it a little bit simpler, you could just calculate your tan beta L first. So if you did that, it would be tan of beta times your L, which we said was 0.05. Now the numbers are nice in this one. What's 1 divided by 20? It's 0.05, right? Why is that nice? Well, then you get that, right? But you don't need this. You could just punch in 20 times pi divided by 3 times 0.05. You get a number, you take the tan of it, perfectly fine, right? So you could punch this in. I'll leave it as tan of pi over 3. Okay. So then we can go back to our Zn and we can plug in all the numbers. 50, ZL is 100 minus J100 plus J times 50 times the tan pi over 3 divided by 50 plus J times, and this is where things get a little ugly here, 100 minus J100 times tan pi over 3. So you just have to take this one step at a time because there's just room for error, because especially here we've got J times that, the whole thing times the tan of that, right? So when we do that J times that, it becomes 100J or J100. When we do J times that J, J times J, minus 1. But then we also have that minus. So really easy to mess up with the minus signs here and that. So you just have to be really careful. Your tan beta L, remember beta is 2 pi over lambda, right? So when you do this tan beta L stuff, maybe it's obvious here because I actually kept it in form with the pi in it. You have to be in radians, okay? Because what are the units of beta? Radians per meter. We're multiplying it by L, which has units of meters. The meters cancel out. You're left with the unit of radians. So your calculator has to be in radian mode for this calculation. So you'd go ahead, you'd punch all that in, and I'll write down an intermediate step and you can check later to make sure that you get the same thing. But it'd be like 100 minus J 13.4 divided by 223.2 plus J 173.2. So take your time with this at home. Make sure you're getting this, okay? Because like I said, all you would do, calculator in radian mode, you'd go tan pi over 3, you'd get that, you'd multiply it by 50. That's a J. You'd add that to a minus J100. That would be the imaginary part up top. That would be minus J 13.4. Your 100, there's nothing to do with it. It just goes right there. 50, 50, bottom. This is where things get a little tricky. What's our real part going to be? Well, the J is going to multiply by that J. It's going to be minus 1, which is going to multiply by that minus 1 to give positive. It's going to be 100 times the tan of pi over 3. That's going to be a real number, which is going to add to 50. That's going to be that. And then the rest is J is going to multiply by 100. So you've got J100. That's going to multiply by the tan of pi over 3. That's going to give you J 173.2. At this point, now you're doing our usual thing. Convert the top to polar, convert the bottom to polar, divide the magnitudes, subtract the angles. Then you have some result in the square brackets that is in polar form, magnitude and phase. You multiply by 50. How do you multiply by 50 if you're in polar form? Just the magnitude, because it has an angle of 0. It's a purely real number. Okay, so at the end of all of that, you'd get something like 17.86 angle minus 45.4. And in impedances, again, you wouldn't be wrong if you left it this way. But unlike reflection coefficient, it's kind of nice if you put it into rectangular form, because then it's real plus j imaginary. And you can kind of visualize that or think of that as more like a resistance, either a capacitance or an inductance. So how would you convert that into real and imaginary? Yeah. So you do 17.86 times the cos of minus 45.4 plus 17.86 times the sine of minus 45.4. It'd be something like 12.5 minus j 12.7. Okay, it is 4:46. I'm a minute over. So I will pick it up here. Do try this calculation yourself. And the first thing we can do is discuss it if anyone has any problems. And when we come back on Wednesday, we will start at part C. All right.